We're going to compare the experimental probability and theoretical probability of a six-sided coin. So first we're going to look at the theoretical probability. A six-sided coin, like it says, has six sides to it. It's essentially a cube if you're unfamiliar with them. 1, 2, 3, 4, 5, 6. And there's usually a dot to represent a number value on it. So 1, 2, 3. The values usually go up to 6, and the dots tend to look like this in your standard die. Oh, did I write coin on there? Oh, geez. I'm going to fix that. Hope I didn't say coin, too. I meant to say die. A die is the singular of dice. Six-sided die. Dice means more than one. A die is a single dice. Okay, so theoretical probability. There are a total of six sides. So probability in theory has a formula that is the number of successful outcomes. I always put two L's there. It's one outcomes over the number of possible outcomes, I believe. Yeah. Or in our case, you could call it the number of sides. There are six sides to a die. So the theoretical probability, I'm going to put a little t here so that you know the difference, because we are going to compare experimental and theoretical. So probability in theory of getting a 1, well, there's 1 out of possible 6 sides, so you have a 1 in 6 chance. And since this we're going to assume is an evenly weighted die, so it's a fair die, the probability of getting a 2 would also be 1 out of 6. Probability of getting a 3, also 1 out of 6. Probability in theory of getting a 4, 1 out of 6. Probability of getting a 5, 1 out of 6. And probability of getting a 6, surprise, surprise, is, in theory, 1 in 6. What about an experiment? Well, experiments aren't always exactly the same. Okay. So we're going to jump over to our random.org here. I'm going to roll 12 different die or 12 different dice or one die 12 times. Click it here, and here we go. And we're going to make a tally of this. Okay. So for our tally, you have an option of 1, a 2, a 3, a 4, a 5, and a 6. So let's see what we got here. We have a 1, 3, 2 3s. So 2 3s. We have 1, 5, 2, 3 5s. 1, 2, 3. We have 4, 4, 2 4s. 1, 2. We have 1, 2. 1, 2 1s. And 2 6s. Wow. So this one came out pretty close to the theoretical probability. I'm going to take a picture of it for our notes. It would be quite helpful. We can take our frequency here. It should show up on the other page. There we go. We'll come back. Okay, we'll make a little bar chart of this. So for our bar chart here, our possible outcomes were the values of 1 through 6. So a 1, a 2, a 3, a 4, a 5, and a 6. And let's see here. 1, 2, that's 3, 4, 5, 6, 7. Okay. We went 2, 1, 2, 2, 3, 2. So 2 1s, 2, 1, 2, 2, 3. So I did it really quickly so that I wouldn't forget it. Double check that. Okay. I know technically I didn't read, so let's do it. We rolled 2 1s, 1 2, 2 3s, 2 4s, 3 5s, and 2 6s. So the experimental probability, so the probability of an experiment, is number of successful trials. We had a little glitch here, so kind of missed the video as I kept going. I'm going to explain what I ended up with. So the probability experiment is the number of successful trials over the number of trials. So I very quickly took all the frequencies here, and remember we rolled the dice 12 times. So the probability, or the experimental probability of getting 1 was 2 in 12, which is an equivalent ratio or equivalent fraction to 1 in 6, the same as the theoretical probability. As a percentage, it's 16.6 repeated. Of getting a 2 was a little bit less. It was 8.3, which actually, now that I look back, I put it in the wrong spot. That should be there. Okay. We ended up getting 2 3s out of 12, same as the theoretical. We got 2 4s out of the 12, same as the theoretical. We got 3 5s, which actually is the same as a quarter, so there's a 25% chance in the experimental probability of getting 5. And the 6 was also the same. So you'll see the experimental probability, for the most part, here, 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 and here was the same. A little low here and a little high here in comparison to the theoretical probability. If you run the experiment many times over, and the more trials you run, the closer all of the percentages should get to the theoretical probability. This is called the law of large numbers. So the more trials we run, the closer we get to theoretical probability. And there's our comparison of experimental and theoretical probability for a 6-sided die. We can take a look at our frequency chart along